Okay.
Speak up if you need to.
Okay. Okay. Good afternoon, everyone. I'm Chris Rebholz from Research Program Management, and thank you for coming to this week's CoolTalk. A couple things before we get started. If you're not already on the CoolTalks DL, please go to Auto Group and look up CoolTalks from Research and add yourself to list number 2, because lists number 0 and 1 are already full. Let's see. All of these talks, the CoolTalks, are all Microsoft proprietary information, so please keep this, feel free to tell your friends and relatives about this as long as they have blue badges. Let's see what else. So today's talk is going to be on the secrets of text anti-aliasing revealed. So thank you, John, for that trick. Our speakers today are John Platt, who has been with MSR for 5 years. He has his PhD from Caltech, and he was the director of research at Synaptics before he joined us here. And our other speaker today is Turner Whitted. And Turner actually helped deliver the very first CoolTalk a little over a year ago. He's a senior researcher. He's been working in signal processing since the mid-'70s. He's been working in text formatting since the early '80s. And as he says, that's about when he started giving this lecture as well. So he's greatly relieved to finally get it down on videotape so he can start referring people to this again. Turner also, this year, became a member of the National Academy of Engineering, which basically makes him one of the 2,300 best engineers of any type in the United States. So, with that, I will hand it over to Turner. So.
My job is to set John up, and I'll do that as well as I can. The interesting part is his. Mine is just intro. So let's get right to the garage door opener here. Other way. Sorry. Okay. Thank you. First, we're going to start off with just a review of signal processing, linear systems theory, other stuff that are fundamental. Then we'll take a break for questions in case I completely confuse everybody. And then we'll get John up here talking about the heart and soul of what we want to get across, which is the particulars of how anti-aliasing is done in Microsoft products. So the system that we're really interested in is this one. We have computers that have font rasterizing software. They have frame buffers. They have a bunch of other stuff in there as well, but this is what matters. We start off with a signal. Take the letter A, for example. That's a signal. We go through a font rasterizing engine, we stick it in a frame buffer, and then ultimately we give up control of it and send it off to a display which we don't own, we don't control, we don't manufacture, and in most cases we don't know what goes on inside of it. The display, which is a continuous device at any level above the quantum level, emits photons into our eyeballs, and that's what we see. So what we want to do is just ignore all those specifics and look at this in a little more abstract terms. Think of everything that we do over on the PC side as a filter. Just run everything through the whole filter and sample process. Think of everything that happens in the hardware once we refresh the display from the frame buffer. Think of that as a filter. Those two filters are what we want to talk about. Question number 1, what's a filter? Well, there are lots of ways to talk about filters. How many of you have ever purchased a hi-fi system? Good, we're all going to be on the same wavelength, so to speak. Sorry about that. That was not intentional. One way to look at filters in terms of response, here we have a low-pass filter. I didn't say what it was. I haven't specified or anything, but we can sit there and look at its terminal characteristics. We take a low-frequency sine wave, run it through the filter, it comes out unattenuated. We double the frequency, run it through, and it comes out slightly attenuated. We triple the frequency, and it comes through pretty badly attenuated. That's the dead giveaway that it's a low-pass filter. And this is one way to characterize it. We just look at the frequency response. In fact, that's the way most people think in terms of filters. The model we use, the mathematical model we use to describe filters is called convolution. Convolution is, by the way, there are no integrals in this talk. No e to the j omega t, no 1 over 2 pi. None of that. This is all intuitive, but rigorous. If your intuition isn't rigorous, then junk it and getting you intuition. We're hoping to do this rigorously. Convolution, in a very simple sense, says if I have a signal, and I've got a very simple signal, it's 0 except for this brief period where it goes to 1. And I've got a filter whose impulse response is just a hat like that, then the way I convolve, or the way I figure out what the response of that filter to that input is to flip the filter over in the spatial domain, which is easy in this case because it's symmetric. You notice I used all the easy cases here. And then I slide that filter along the spatial axis and multiply the input signal times the filter, and then take the area under the curve. In other words, I'm integrating the product of those two, and that's convolution. So if we look at the response, the actual pulse that comes out of this filter, if we convolve this far and we run it this far, this is the response. You look at that area up there, that corresponds to this. We go a little further, we're further up the curve, and so on until you hit the peak and then come back down. So if I have a filter with this response and I just ping it with that pulse, then this is what comes out. And obviously this is a low-pass filter too. By the way, we characterize filters with their impulse response. Go take a big sheet of metal and a hammer and slam the sheet of metal, and what you hear afterwards is the impulse response of that sheet of metal. It's just as a sort of exercise for the reader. But that completely characterizes the response of that filter. So that's convolution. There are a few things that it's useful for. One is that any time we have a system that's doing filtering, we can express the result as a convolution. More importantly, if we have a couple of filters cascaded, for the Unix hackers, that means there's a pipe connecting them. If they're cascaded, we can take the aggregate transfer function. We can convolve the two filters against each other, come up with an aggregate response, and use that as a response for the combined filters, which is useful. There's something else that I haven't gotten to yet that we will get to, and that is the dual representation. We've been doing everything so far, this entire discussion has been in the spatial domain, along that horizontal axis. It's very useful, especially if you go out and buy speakers or amplifiers for your hi-fi and you see all those plots that the salesman shows you. Very, very useful to think of the response in the frequency domain. The frequency domain and spatial domain representations are duals of each other. They're related by the Fourier transform. It's invertible. I can take a frequency domain representation of the signal and recover the original signal just by going through the inverse Fourier transform, as long as I don't throw away the complex components. But I said we're not going to get into any math here, so ignore the complex components. More importantly, for intuition, there's a theorem that says that convolution in the spatial domain is equivalent to multiplication in the frequency domain and vice versa. Multiplication in the spatial domain is equivalent to convolution in the frequency domain. We'll use that because it really helps our intuition to take advantage of that. And we'll see that in a second. Now, there's one other property of linear systems that we like to use as well, and that is superposition. We just, because it shows up so much, I just want to mention it. I'm going to use a test signal in the rest of this talk that's equal to a sine wave minus 1/2 its second harmonic plus 0.3 times its third harmonic. And what I get is this sort of really bad sawtooth approximation over on the right. And of course, as you know, you can represent any signal as the sum of sinusoids. That's the beauty of sine waves. Now, there's something else that happens in linear systems. If I take the individual components and run them through a filter and then sum the results, I get exactly the same thing as if I had summed the signals and run it through the filter. And that's useful too. Now, we'll actually, the only use we're going to make of this is to recognize the identity of those original signals when we look at the frequency domain representation. And the fact that these are orthogonal, aren't they? Yeah, these are orthogonal, and that becomes handy, just as a way of understanding what we're seeing in the frequency domain. So let's look at the frequency domain. Here's a continuous signal. Same signal I just showed you. It just repeats ad infinitum. In fact, assume everything repeats infinitely, which is a little strange when we're talking about displays. Wishful thinking on my part that they would extend infinitely. But for the sake of understanding this, let's assume that. Now, if I take that continuous signal and take a Fourier transform of it, this is what I get in the frequency domain. Notice what we see. We see the fundamental frequency, that original low-frequency sine wave, represented here. This is 0 frequency. Here's that fundamental. Here's the second harmonic. I'm only showing absolute values. I'm showing the square root of sum of the squares of the real and imaginary components. So what I'm seeing is only positive, even though that's minus 0.5 times the second harmonic. And then here's the third harmonic. So you can easily see the original signals here, and the spectrum makes sense. Mathematically, you end up with a negative frequency as well. Just, ignore the negative frequencies. You don't have to, just nice and symmetric. And that is the spectrum. So it's kind of useful. I can look at the spectrum, and it's the thing I like about this is I may not recognize what the components of that signal are just by looking at it in the spatial domain. But if I look at this, I can tell you exactly what's there. It's for an engineer, it's an incredibly useful way to look at signals. Now, I'm going to do something really wicked to that continuous signal. I'm going to sample it. We're all, we work on computers and we deal with samples. I haven't dealt with analog computers since the 60s, so presumably everything we do is sampled. Sampling, by definition, is a multiplication of an impulse train, an infinite impulse train times that continuous signal. You can see it up there. I've multiplied this chain of taking that continuous signal and just multiplied lots of impulses. Multiplication in the spatial domain is equivalent to convolution in the frequency domain. As a consequence, when I convolve the Fourier transform of the impulse train, which itself is an impulse train, when I convolve that with the original spectrum, I get replicas of the spectrum to plus or minus infinity, which isn't particularly good because what I really want is that original signal. The question is, how do I get back to this original signal? By the way, those replicas are spaced at the sampling frequency. So if I sample that at f sub s, the spacing between these replicas is equal to the sampling frequency. This should be reviewed for most people, and run into it pretty fast. I want to get the original back. Well, here I can see in the frequency domain, this is my original signal. I just want to recover it. In other words, I want to get rid of this and get rid of that, and that's all I got. So if I go in there and multiply it by a window that just eliminates everything but my baseband signal, then I'm going to get my original signal back. Well, this is multiplication in the frequency domain, right? That eliminates all the replicas. If I do that, that means that I can convolve with the Fourier transform of this, which happens to be a sine x over x function. If I convolve the sampled signal with that function, then I'll get my original back. In fact, I've chosen the cutoff frequency for that window function to be 1/2 the sampling frequency for a very good reason. It gives me the maximum amount of bandwidth available inside of that window. And if you remember the sampling theorem from sophomore year, it says that any signal can be recovered from its samples if there is no frequency in the original signal above 1/2 of the sampling frequency. And it's just completely obvious when you look at it in the frequency domain. Let's play some games. Let's increase the sampling rate. I'm sorry, let's increase the frequency content. The sampling rate stays the same. Remember, we're talking about displays. The resolution is what it is. We can change the frequency of the signal. I just multiplied the fundamental frequency by a factor of 4 look what happened. The signal started creeping out towards its replica, which gets a little scary. Here's the 1/2 the Nyquist rate. This is the Nyquist rate, 1/2 of the sampling frequency. If I go up to a factor of 6, something really weird happens in that the replica starts folding back down into my original baseband. This signal right here, which is really the third harmonic of this replica up here, is masquerading as a lower frequency signal. And if I increase the frequency, it will creep further and further and further. It's a high frequency signal pretending to be a low frequency signal. That's why it's called an alias. Aliases are bad. That's the whole point of this talk. How do I get rid of that alias? Well, I can't. At this point, I've got a sample signal which has frequency components that fold back down. There's nothing I can do at this point to recover that original signal. I've violated the sampling theorem. So I have to do something different. By the way, everything I just talked about has nothing to do with anti-aliasing. This is reconstruction. In other words, I've got a signal, I sample it, and I reconstruct it from its samples. I've gone through, this filter is not the anti-aliasing filter. We'll come back to that in a second. Now, let's go back and say, how do we avoid this? But let's look at a signal that's more interesting. I'll take the letter O. I could have taken, I thought about M, but it had too many pieces in it. O is about as simple, well, I could have taken, but that's boring. So we'll draw a straight line through O, and what we get is this signal up on top. You see it's white. It's at a max right up till you get to the boundary, and then it goes down to 0, and then comes back up at the hole, and then goes back down. So everybody sees that that's a cross-section of the letter O. Now, if we look at that in the frequency domain, lo and behold, this thing has infinite extent, which is exactly what we don't want to happen, because if we sample that, we'll get aliases no matter what. We can increase our sampling rate, but we pay money for that. Ask Bill. Bill's got the highest sampling rate on campus and probably the most expensive one, too, at 4K by 4K or whatever he has on his desk. And it's still not high enough because this is infinite. This frequency has infinite extent. What we need to do is filter out the high frequency components prior to sampling. So what we do, if we take the letter O over here in the spatial domain and convolve it with an ideal low-pass filter, you'll see the response here. It's much more easy to understand in the frequency domain. Here we took that infinite extent signal, multiplied it times this window. Notice that we got no components above here, no components below here. That's a signal we can sample safely, assuming that we're going to sample at twice this rate. That's the key. So you sample it, you filter it before you sample it, and you've got to filter it after you sample it to reconstruct the original. If you do that, then you're going to get the original band-limited version of the signal back. Now notice a couple of things, that if you use this ideal filter, you get kind of weird distortions. John's going to talk more about that later, talk about what you can and can't get away with in a practical sense. So that's the introduction to anti-aliasing. There is a big question. Well, all of our signals have digital representations. How in the world are we going to do filtering on a continuous representation before we sample it? And the answer is we do an informed cheat. And that is we normally sample at a much higher resolution than we're actually going to display it at. And we do a discrete approximation to the filtering. And then we decimate, we resample at the display resolution. And that's a good enough approximation if our original supersampling rate is high enough. There are other schemes that are not as broadly applicable. In special cases, you can pre-compute a closed-form solution to the convolution and store that and then apply it. And superposition helps here, especially if you can add the signals. This is hard to do, and not many people do it. Most people, in fact, routinely, internally in our software, do the oversampling. Now, I've covered everything except the display. This is a optional slide, so you can kind of zone out if you don't want to talk about it or think about it. But the frame buffer stores samples like this. What happens before it gets to the display? What's the nature of the display? We don't own this. Nothing we do in our software is going to affect this, but we need to understand what happens. What happens is that we take the result, the output of the frame buffer, we go into a register. If you're a signal processing guy, that's called a sample and hold. We clock it into the register. It stays in that register for a clock period until the new one gets clocked in. The fact that we're digital over here on the left and analog on the right is totally irrelevant. In terms of the theory, it's all sample signals. So here we go through a sample and hold. Then we go through a connector and a cable and an amplifier and a bunch of circuitry, which, if you've ever looked at it, it's a mess. We're going to assume that the D to A converter has a slew rate that's higher than our clock rate, significantly higher than our clock rate. We're going to assume that connectors have really good characteristics. We're going to assume there's no resistance in the connectors. We're going to assume that the analog display circuitry has infinite bandwidth, and we get right back down to the pixels, the physical pixels. This is for an LCD, a monochrome LCD. You've got these little square things on the screen. That represents a filter. Notice that the width of those square things is not quite as wide as the whole sampling interval, and the reason for that is that you've got to have dark space between the little squares. Get out a microscope, look at your LCD sometime. If this were a CRT, they'd be Gaussian blobs, because that's what the electron beam gives you. I'm talking strictly about LCDs. If it's a color LCD, heaven help us, but John will talk about that later. Now, that has a frequency response. If you look at this, this is the spatial response, which is the impulse response for that particular arrangement of the pixel. This is the impulse response for the sample and hold. We know that we've cascaded those. Therefore, if we convolve this with this, we get that. And if we take the Fourier transform of that, we get this. And by the way, that's actually a negative lobe. I'm showing, again, I'm just showing amplitudes. I haven't, everything's positive in my plots. So I've got a reconstruction filter that isn't quite what I'd like. It's as good as I can get with the current hardware. It cuts off the high frequencies prematurely, and it leaks aliases in a way I don't like. But that is what I have. Okay, so now we've covered the notion of anti-aliasing. Let's just go back through this. We've covered the whole point of pre-filtering and sampling, the anti-aliasing work, and then we've covered reconstruction, which happens at no cost to us in the hardware, although suboptimally. Those are the two filters that we apply every time we display something on the screen. The part we control is this. John's going to talk about the details of that. Right now, I want to stop briefly, ask for questions before John stands up.
Why is it okay to throw away the high-frequency components when you do your initial filtering?
Why is it okay to throw away the high-frequency components? It's not okay to throw them away, but you can't have them. You're not, I mean, the fact is you can't reproduce them. You will get degradation. You will see a blurred picture. But there's no way that chain will allow it. This will not support those high frequencies. Rather, it's much better to throw them away than it is to have them masquerade as low frequencies and introduce jaggies or other artifacts. No, it's not okay. You want an infinite resolution. You know, you really want infinite resolution. But this is the best we can do. Other questions? Okay, John.
Okay. Can you hear me? Okay. So now I'm going to talk about specifics of text anti-aliasing. Everything Turner talked about was totally generic. It could be sound, it could be video, it could be images. Now I'm going to tell you about text. And unfortunately, text is different than generic or image display. Or maybe it's fortunate. And so I'll go into the details of how it's different and tell you how we actually sort of warp our anti-aliasing system to adapt to it. that's the first part of the things I'll talk about. And then we'll take a break for questions. And then we'll go into something called display-specific anti-aliasing, which is also known as clear type. In clear type, we use the spatial structure of the LCD. The reconstruction function that Turner talked about is very special in an LCD. And we're actually going to sneakily use it to gain some of that resolution back. So we want to try to get as much resolution as possible. So we're going to try to use the spatial structure of LCDs to get it. So first, let's go to the text-specific anti-aliasing. So how is text different from generic images? Well, there's several differences. One, text comes as glyphs, right? The letter A. And so they have predefined objects with certain meaning, and we can actually manipulate them sort of object by object, and I'll touch on that briefly. Unlike generic images, they're also defined as a mask between foreground and background colors, or foreground and background images. And again, that allows us a certain savings. And there's an unfortunate fact about text is that it often occupies the entire dynamic range of color. You're typically, like here we're looking at white on dark blue. So the white is slamming all of 3 color channels to be maximum. So within this little text-specific anti-aliasing thing, I'm going to tell you about how to adapt anti-aliasing to cope with those differences. And I'll tell you some tricks that we've come up with that kind of fix some of the problems when you do number 1. So now we're specializing to text. So here's the goal of a font display. You have some ideal font shape that you've very carefully designed, and you'd like to display it on the screen in pixels, and you'd like to choose all of the values of the pixels so that it looks as nice as possible. So here are the steps. I'm going to go over it briefly. I'm not going to talk about each of these in detail. I'll dive into some detail in a minute. So the first step when you have a font, it's optional. You don't always use it, but you often do when you have static text. Is called hinting. You may have heard this term. What is hinting? Well, hinting, one reason why text is different than images is that you can warp text, and you can warp an M. You can kind of squeeze it or stretch it, and it still means an M. You can't really do that to just arbitrary images. Well, you're not really allowed to in signal processing. But here, since we have this beautiful M isolated, we can kind of manipulate it and warp it to make it behave better further down the chain, to make it be less jaggy, for example, or higher contrast. So hinting, I can't really go into much more detail than that in the time, but that's sort of the purpose of hinting. Then we're going to go down the path that Turner talked about. We're going to do this dramatic oversampling, get a little tiny bit of aliasing out, but that's how we're going to do it. We're going to start by sampling those outlines at a high resolution, like 4 or 6 times the pixel resolution. Now we're going to do the anti-aliasing. We're going to filter the samples down to the pixel resolution. That's the anti-aliasing step. In fact, it's the pre-filter plus the sampling. And then now we're going to, after we've got the pixel resolution stuff, we're going to composite between the foreground and the background color. And I'll talk more about that in a minute. And then eventually, we're going to correct for nonlinearity in the display. So displays have nonlinearity, and I'll talk about that too. But these are the steps. So let's talk about one of the differences between text and images, which is that text is defined as an alpha mask, right? Glyphs don't really have any innate color. They just have opaqueness. And in fact, we call that opaqueness alpha. That's how it's measured. And for a perfectly opaque glyph, alpha is equal 1 inside the glyph, which means use the foreground color. Alpha equals 0 outside the glyph, which means use the background color. And so this is fine and good, but how do you actually compute pixel colors? Well, you compute them through a process called compositing, where you compute the pixel color equals alpha times the foreground color plus 1 minus alpha times the background color. So it's kind of a blend. So you always are in between the foreground and the background color. Now, if you wanted to be really fully correct and do correct signal processing, what you would do is you'd first composite, and you'd get 3 images, red, green, and blue, and then you'd apply anti-aliasing to those 3 high-resolution color images. But it turns out you can speed things up by a factor of 3, and so we often take the shortcut, where we transpose the 2 steps. We're going to filter the alpha image. That's only 1 image, not 3. And then with that filtered alpha, we'll composite. That's not quite right. It turns out to be perfectly correct if you have a perfectly constant foreground and a perfectly constant background. And if we don't, we just pretend we do, and we just go ahead. So we cut the work down by a factor of 3. So here's another wrinkle with text, which has to do with the dynamic range of the colors. So here, the green, this is similar to something that Turner drew. the green is is a slice through a stem, like a 1. Say I'm more boring than Turner. I decided to just have a 1 instead of an O. And here's a good anti-aliasing filter, sort of that magic shape that cuts out everything above a certain frequency and keeps everything below. Well, that's the ideal thing. If I convolve them, you actually get something like this blue curve here. And there's this unfortunate problem, which is here's 0, right? So if I did the signal processing correct thing, I'd have to suck light in from the display. Well, I don't have any, I have photons, I don't have darkons, so that's impossible. So in fact, you have, this is just working through, you get these undisplayable negative pixel values. So we really can't, sadly, because text tends to slam the dynamic range, you can't use negative lobes as much as you would like to. In fact, here's another thing. Hopefully this looks good. Does this look good? Yeah, you can see this. So if I take, in fact, this is just another way of saying something in the same slide. So here's the beautiful stem that's 1 pixel wide. If I convolve it with a perfect anti-aliasing filter, but then cut off anything below 0, which is sort of the expedient thing, you get this kind of ugly thing. Here's the stem. It's perhaps properly anti-aliased. You get a nice black region, and you get this little gray blip. It's a ring. It's called ringing. And that's kind of unpleasant precisely because I can't display anything darker than dark in there. So that makes these look odd. So the negative filters, the negative lobes, not being able to do negative lobes mean you can't have a sort of second positive lobe out here. We have to just stick with filters with positive weights only. Oh, I'm sorry, I actually used an undefined term. A lobe in signal processing is a portion of a filter that's either all above 0 or all below 0. So what do people do when they try to filter? When they try to do anti-aliasing text? Well, the first impulse everyone has, I guess that's also a pun, but is use a box filter. So how do you use a box filter? Here's a box filter. It looks like a box. It's, for example, 1 pixel wide. And it says, please convolve this shape with my high-resolution samples, and then sample once per pixel. A totally equivalent way of thinking about this, which is why people tend to do it, is, oh, you've got a pixel. It's a box 1 pixel wide, right? And there's some glyph that intersects it. Let's just measure the fraction of the glyph that overlaps the box. That seems intuitive and reasonable. Unfortunately, it's not quite the right thing to do because of all the signal processing stuff. So if you want to do box filtering, you should at least resist the temptation and think about it. And let me explain why it's a suboptimal thing to do. And it's going back to this frequency response. Remember, back to Turner's part of the talk, I can take any linear system like a convolution by a box filter and just look at its frequency response and try to understand what's going on. So here's the frequency response. Essentially, if I put a sine wave in at different frequencies, I'll get a sine wave out. I'm going to ignore phase. You get a sine wave out of some size, and that's what the blue line is, and it looks like this. Now, ideally, remember from Turner's part of the talk, there's a magic frequency. It's called Nyquist. Here I've just plotted as 1. Anything above here gets aliased and causes jaggies. So ideally, I'd like this red line. I'd like what they call the brick wall filter. Everything that's bad gets eliminated. Everything that's good gets preserved. Well, you can't have that without an infinite amount of compute. But in this box filter, unfortunately, it's pretty far away from optimal, right? So instead of 0, there's still a lot of power that kind of leaks through. And then that gets sampled, and that makes jaggies. So box filters they do part of the job. They certainly damp this down, but they don't do a good enough job. There's actually alternatives. Another alternative that we found is the single lobe of that ideal sync filter. So here's that same shape in green. You can see it's almost like the box filter. It's not quite the same as the ideal low-pass sync because we're going to actually slightly shrink it. We're going to use something a width of 3/2 pixel. And so if we take this green filter and run a bunch of sine waves into it, we can look at its response. And we can see that in the forbidden region above Nyquist, well, it's about the same as the box filter, but then it represses the bad frequencies more. And that's better. So you get less jaggies. This plot tells us that you get less jaggies with the green than with the blue, purely from the frequency response. What is a sync filter? Oh, I'm sorry. A sync, an undefined term. Ugh. Okay, sync is sine x over x. it looks sort of like this. It has infinite extent. And so what I'm doing for a one lobe of it is I'm just truncating this off because these are all negative and bad. And I'm just using this, but then I shrink it a little bit. Okay, so you may be wondering, Turner and John seem to be plotting an awful lot of 1D plots. Well, that's because they're lazy, and it's easy to make 1D plots. It turns out that all this theory we're talking about completely extends to 2 dimensions. You can have 2-dimensional filters. You can do 2-dimensional convolutions. So instead of passing one thing past another, you can pass it in sort of all different ways. 2D filters, all the linear system theory works. 2D filters have 2D frequency responses. You can feed in a sine wave, but now in addition to having a frequency, it essentially has a direction too. And you can make little 2D frequency response plots, which are like little 3D plots. The only problem is, it's not really a problem, is that 2D filters are computationally expensive. You know, a 10 by 10 filter, if that's the size of the samples, take 100 operations instead of a 10 by 1 filter, which only takes 10. So what a common thing we tend to do is do something called, make an approximation to the beautiful 2D filters with something called separable filters. So first you filter in X, and then in Y, or the other way around, it doesn't make much difference. And then we only need to think about sort of 1D filters and 1D frequency responses, and we can still talk about aliasing individually in each dimension. It's not quite right, but this is all I'm going to talk about in 2D. So just trust me, we're going to use separable filters and everything will be fine. So let's use these positive-only filters. Great. Are all the problems solved? Well, not quite. Positive-only filters cause lots of gray. Well, why? Well, what is a positive filter? Like, what is a box filter? A box filter is an average of a bunch of samples, right? Well, what happens if I tried to just average a bunch of white and a bunch of black, a bunch of 1 and a bunch of 0? Well, obviously, I'll get some number between 1 and 0, which is gray. So what tends to happen is that positive-only filters tend to wash out the characters. Everyone likes nice high-contrast display, but then this annoying anti-aliasing comes in and makes everything look gray. So that's kind of annoying. So it isn't just happening on black and white. It could be for any color. Just the foreground gets kind of less intense and gets sucked back to background. So what do you do? Well, here's a thing which isn't quite proper, but it works really well. You use a nonlinearity to combat gray. The reason why it's considered improper is that in signal processing, you can see that everyone relies so strongly on all these frequency plots that totally breaks down if you're not a linear system. But we'll do it anyway because we want to make a nice product. The idea is you gently push the filtered alphas towards the foreground using a function that kind of looks like this. So if you say, well, gee, I want to be halfway between, really, you bias it a little bit towards foreground. You're like at 0.7. Now, as I said, it's hard to analyze with the filter theory, but empirically, it doesn't really seem to affect the aliasing too strongly, and it definitely helps with washout. In fact, let me show you an example. Back in Win2K, and in fact in NT4, we were shipping with box filtering, and what you do when you get with box filtering is you get the stuff on the left. Now, there's a mode in WinXP called Visio mode, because I think Visio requested it. It's in GDI+. That's the stuff on the right. The difference is here we use the 1-lobe sync filter, and we use that gentle push towards foreground. And you can see the difference. Look at like 6 through 10 point. It's kind of gray and washed out. And also, there's funny stems that are kind of like strangely dark. That's the aliasing. That's the jaggies. Whereas here, it's much more smooth and gray and less jaggy. I don't know if I have a little animation display, but I think I'll skip that. It also makes nicer animations. So I'll stop here. And, well, let me just summarize for just text-specific anti-aliasing. The goals are generally the same as generic anti-aliasing. You want to get rid of both aliasing, and you don't want to introduce blur, but you don't want to spend much CPU. But unfortunately, you can't do all 3 of those perfectly. So we have to find some way to engineering compromise. When it comes to text, you can't use negative lobe filters because it causes ringing and these negative numbers, and it's all bad. But you aren't forced to use the box filter. You can use something better than box. And you can use a gentle nonlinearity to sort of combat font washout. So that's the first part, and I'll have some questions.
Yeah, how do you find out the alpha? How do you take the alpha into consideration? Basically, how do you find the particular value of alpha to be taken?
Oh, okay. So let's see if I can zip back here quickly. I'm sorry. The question is, how do you find the alpha? And hopefully, I can answer the question. I hope I understand. So the alpha inside. Okay, we have this infinitely high resolution glyph. Typically, if it's opaque, the alpha is 1 for that glyph, and outside it's 0. We then sample at, say, 4 times per pixel. Each of those samples, again, has alpha equals 1 if it falls inside, or alpha equals 0 if it falls outside. Now we filter. So the filtered alpha is a weighted sum of all of those high-resolution alphas. And now, using that filtered alpha, we composite between foreground and background.
Does the thickness of the stem have anything to do with aliasing?
Yes. Sorry. Does the thickness of the stem have anything to do with aliasing? The thinner a stem is, well, you get 2 problems. The thinner a stem is, the more high-frequency content. There's another trade-off. There's always these dualities when you do with frequencies. A smaller something is in the spatial domain. The larger something is in the frequency domain. So as you shrink a stem, you also you bloat its frequency response. So it'll tend to alias more and more. So it's just harder and harder to kind of display very fine details, right? Because you don't have the resolution on your display. The other thing that goes wrong with really thin stems is the resolution of the display fixes the size of your filters. You're supposed to anti-alias. Remember, you're supposed to cut out things after the Nyquist. The Nyquist depends on your display resolution. So you're stuck, right? As you make the stems thinner and thinner, less and less of your filter gets overlapped, so the numbers get smaller and smaller. So instead of disappearing, well, it disappears, but it doesn't shrink. It turns gray and disappears. And that's not quite what you want. So that's part of what hinting is for. Hinting says, you know, this is awfully thin. I'm going to kind of go and stretch it out to make it be thick again.
My question was in that comparison you showed between Win2K and Unix was exactly the same font and hinting?
Yeah, yeah. In fact, oh, sorry, wrong way. Yes, exactly the same font and hinting was those had exactly the same samples. In fact, exactly the same high resolution samples. I don't know. It came from Quality. I don't remember. Let's see. Was the thing? I think there was hinting. Where did it go? There you go. I think I actually turned hinting off because when we were designing this, Visio didn't want hinting. They wanted just arbitrary fonts. Mike, who asked the question, he asked if there's any hinting. He's actually the hinting expert. There's a little thought balloon over his head. He said, that doesn't look right. That looks really bad. How can you possibly? Well, I turned hinting off, so these are both for no hinting. And actually, Win2K did look better than this. This is unfair to those who worked on Win2K.
The negative lobe, suppose your background was light gray,
Mm-hmm.
then you could make the negative lobe.
Yes.
Does it look better?
Yes. I'm sorry. Question is, gee, you're complaining because you're thinking of black and white. Does it look better if the background is slightly light gray? Does it look better? Yes. You get a little, if you have black on light gray, you get a little tiny white border around the font, and that looks good. It makes it look sharp and good. So but we're trying to make the same code path that works for all possible colors. There's actually a reason for that in software, because under XP, the alpha for glyphs are pre-filtered and cached before you ever know the color of the fonts. So you put them in memory, you filter them once, you put them in memory, and you just leave them there in something called the font cache. And so you can't really filter it saying, oh, I know that it's white or black. So it's kind of unfortunate. I don't know if that's still could be true in Avalon. We can ask the Avalon folks.
But also, doesn't the reduction in contrast caused by raising up the black reduce the legibility back to where you were?
You can't. Right. You can't do that in general. You can't say, well, the question is, can you do that in general? Can you shrink white in and make it slightly gray, and shrink black in and make it, slightly less black? It does hurt the legibility a lot. People desperately love font contrast. That was the hack behind here, the nonlinear hack that pushed you towards foreground. And if you eat into that to try to get nice, sharp characters, people just hate it. It's hard to read and
less tonal legibility.
I believe I believe that's true. I believe it makes it less total legible. I know that people hate it because they buy a special, high contrast display, and then if the software goes, heaves 10% of it out, they tend to get kind of upset. Any other questions?
Is there any way to combine that filter that you discussed with the boxing filter? The reason I'm saying is that if the text is perfectly hinted, then the alpha direction is, so is there any way to cut off like very lightly gray colors? For example, if I'm anti-aliasing the black foreground, white background.
And you have a very thin stem.
Yeah, and there is always like if it's not perfectly grid fit, the stem, then there is always like very light colors.
So the question is, can you cut off the very light gray? No, unfortunately not. There's a lot of unusual fonts like Vivaldi, which have these long, swoopy, very thin things. In fact, there's in the hinting code itself, there's I forgot what it was called, the dropout control. Is that right? There's something called dropout control where you can actually, it becomes a very thin stem, and you could miss the grid entirely. And so they just, without anti-aliasing, if you're just in black and white mode, it just plops a pixel down there because it's very important to have continuity. So you can't go through and have statement saying, well, if anything is really, really faint, just cut it out because that causes breaks in your characters and drops serifs, and it does sort of terrible things. One last question, I'll go on.
What would a Gaussian filter look like in this case?
Okay. So Gaussian, when you deal with signal processing, you just memorize the Fourier transform of all sorts of things. It turns out the Fourier transform of a Gaussian is a Gaussian. And so it depends on what size Gaussian you'd like. You can imagine fitting a Gaussian, and a Gaussian would kind of come up like this and look like this. So there'd be a bit more aliasing here. It would also have to kind of extend further. So a Gaussian filter would have to extend further. And so, of course, you pay for every pixel you touch, for every sample you touch. So you want to kind of make it have finite support. So
you don't get the rigging, but you get more of a fuzzy edge.
Right. Well, it depends on exactly how sharp of a Gaussian you use. And where fuzziness comes from, okay, so this is where aliasing comes from, letting stuff in here. Where fuzziness comes from, I can't reach it, is the gap between the top red and any filter. And so the bigger that area is, the more fuzziness, the more blur you get. So it really depends on what size Gaussian you use, right?
Could you amplify and clip to get rid of that?
Amplify and clip. You could. There's a weird interaction between the nonlinearity and that I suggested, the push, the foreground push, and any sort of filters, but it's not terribly well understood. But this seemed to work very well and has finite support. In other words, it isn't terribly wide. You only have to look at 1.5 pixels worth of stuff, so it's pretty cheap. Okay, let me go on because it's 7 minutes to 1, and I still have 15 minutes worth of stuff. So, oh well, if you get up at 1, I won't be offended. Let's see. Okie dokie. Okay, let's talk about ClearType. In ClearType, ClearType was originally invented back in 98 and 99, and it was joint work by a bunch of people, some of whom are in this room, some people from ebooks like Bill and Greg, and some people from GDI like Claude and Bowden, and some people from, and Bert's from ebooks, and some people from Microsoft Research, including Turner, and then lots of other people since then. So it's a big joint effort all across the company. So it all started with, I guess, Bert and Bill and Greg asking the question is, can we get extra resolution out of an LCD? Because after all, you could, okay, so what do LCD pixels look like? They look like this, right? They always look like that. There's always, well, for a particular display that has this pattern, every pixel on that display will have red, green, and blue. Some people are perverse and make blue, green, and red, makes life difficult, but let's assume that it always looks like this. Well, you have like 3 little light bulbs per pixel. And you say, with 3 little light bulbs, maybe you can get more resolution out. Well, you can, but only if you're colorblind, right? So if I were colorblind, I would see this, and I would say, well, I can manipulate those light bulbs. One of them happens to be kind of dark. And I can get 3 times as much resolution. So ClearType is sort of less extreme than that. There's a trade-off. I could start squeezing more resolution in, but I start making color errors. And the right question is, how do I do this trade-off between resolution and color errors to increase the resolution a little bit, but not to be too objectionable in terms of color? So let's go back and review, just briefly again, generic anti-aliasing. Generic anti-aliasing, okay, temporarily forget I talked about alpha filtering. I want to think about anti-aliasing on the 3 color channels. So what is this? This, again, is a horizontal slice through my image with text in it. This is the blue scan line, the green scan line, and the red scan line. So there's some sort of blue stem here. There's a black stem here. Now, when I filter, and then when I pre-filter and then sample, it looks like this for 1 pixel. Here's the pixel I'm trying to find the color on. There's some region of the input that I compute a weighted sum over. And I compute the same weighted sum over the same region on the red, the green, and the blue images. And then I compute, in fact, I just do them independently and just compute a color for that pixel. That's pretty easy. What happens with LCDs? Well, there's this problem that Turner alluded to, which is the reconstruction. The reconstruction filter of the LCD is incredibly wacky. You see, because the standard anti-aliasing assumes that the pixels have no internal structure. And so there's nothing odd when you reconstruct, when you try to display, there's nothing odd that happens. But LCDs do have internal structure, right? For this display, red is always to the left and blue is always to the right. So I take this carefully computed sample that I compute here, and then I strangely move it over there. And vice versa for blue. So red and blue are a little bit screwed up. And so, there we go. And so you get this position error. Depending on the color of your object, you actually get a different position. So if I had a green A, it would show up perfectly. If I had a red A, it would be shifted a third of a pixel to the left. And if I had a blue A, it would be shifted a third of a pixel to the right. And now you might say, well, big deal. Who cares about a third of a pixel? The problem is that if you have anything that isn't monochrome, it has all 3 colors at once. So it looks blurry, right? It's got this extra blur, and that's kind of annoying. Now, you could chalk this for a long time. For many years, people chalked this up sort of like what Turner said. Oh, it's just the hardware. You know, what can we do? You can't really do anything. But then we decided to do something about it. And so the first thing you might decide to try, this isn't the first thing we tried, but this is a conceptually easy way to explain it, is let's generate a sample for each subpixel at the location of the subpixel. So this is the spatial location of the red subpixel. And so we're going to sort of drill to the red image and then take a sample there. So there's no position error introduced. Same thing with green. I can drill upwards to green and take the sample there, and drill upwards to blue and take a sample there. And this introduces no position error. So actually, it should be sharper. Well, it is sharper. There's this problem. If you actually try doing this, you get what I call circus fonts. You get all these weird colored fonts instead of, say, black on white. And there's a reason for that. And it's a problem, which I don't think anyone had actually talked about before. It's called color aliasing. What happens if we take a 1 cycle per pixel black on white sine wave? So it has all 3 colors in it. And we do this drilling. So at the red location, we ask what the value is. At the green, we ask what the value is. In the blue, we ask what the value is. In other words, we're going to just sample without filtering. Well, you can see that the red is always on, and the green and the blue is always dark. So what you get is red, right? You try to display a thing that wiggled, and you got a color. Well, and in fact, you got a color of a different frequency. That's aliasing. We've aliased a black and white sine wave at 1 cycle per pixel down to something that's 0, at frequency 0. So there's an analogous thing. So just like in anti-aliasing, you have to say there's some bad frequencies that cause weirdness when you display with normal sampling. There's some bad frequencies that cause weirdness when you do displace sampling. And we have to go and stomp on them by using pre-filtering. So it's just like a normal anti-aliasing, except with colors. So here's what you do. This is how ClearType works. You pre-filter to get rid of the bad color aliasing. And here, the bad things happen at 2 times the pixel Nyquist. That 1 cycle per pixel is a bad frequency, so stomp on it. But we actually want to keep the frequencies above the pixel Nyquist because we actually do have 3 little light bulbs per pixel, so we can actually try to sneak more resolution in. So we're going to try to sneak more resolution in above the pixel Nyquist, but make sure it cuts off by 2. So we're going to do that pre-filtering, and I'll show you filters to do it, followed by displace sampling. So remember, so we're going to do the pre-filter, And then we're going to sample the filter output at the subpixel locations, not at the center of the pixel. And this should all work and be nice. This is just a diagram of the RGB decimation where you apply a filter to the red, sampled at the red location, apply a filter to the green, sampled at the green location, apply a filter to blue, applied at the blue location. Oh, by the way, I sort of took a side turn into red, green, and blue, but just like in standard anti-aliasing, we use the same trick. To save a factor of 3, you only have one image. You start with a high resolution alpha image, which is 1s and 0s, and then you compute, you apply 3 filters per pixel that are displaced, which you then get 3 alphas per pixel. So you've got to do compositing with 3 different alphas. You can't just use 1 alpha per pixel. You have to use 3. And so that's sort of how it works. So which filters do you use? Well, you can either have a 1 pixel wide box filter. So same diagram again. I'm just doing a filter, a frequency response. This is the pixel Nyquist, but we know that this is the bad place. So all the good clear type filters block out these bad frequencies. But there's another additional thing, is that you can actually sneak good frequencies in up to the point where it becomes bad, has bad color errors. So this is the extra resolution that clear type brings you in. So you can get, a factor of 1.5, 1.4 in resolution. Oh, I should explain what the 2 filters are. Blue is the 1 pixel wide box filter, and green is actually a 1.63 pixel wide sync filter. Why? Well, because that makes that 0 right smack on the bad spot. So that's where the weird number 1.63 comes from. It turns out there's a trade-off. This one has more aliasing, but has more resolution. This one has less resolution, but less aliasing. Actually, clear type ships with the box. What about 2 dimensions? Remember, there's this annoying problem with 1 and 2 dimensions. Well, we're going to use separable filters again, just like in the standard mode. Parallel to the stripes, which are typically vertical, just use standard anti-aliasing. There's nothing weird going on. If I just look up and down one stripe, it just happens to be a monochrome display. So just use the 1.5 pixel, 1 lobe sync filter parallel to the stripes. And then perpendicular to the stripes, which is typically horizontal, use either of those 2 filters, like the box filter, and use display sampling to get the extra resolution. And, oh, by the way, you can remember that trick of pushing the alpha towards 1? You can still use that with clear type. It makes it look a little bit nicer. So here, now, of course, it'd be really great if I could show it to you right on the screen, but I have no idea what the pattern. Actually, it looks like it's a bear pattern, but I have no idea what the pattern is on the display. So I had to make little Faco pixels that are big. So this is the one time where sitting at the back of the room is actually good, because you actually can. It's sort of like what you might see in real life. So up here, this is the word font with no filtering. You can see it. You can get jaggies, and this is what happens when you ask for nothing. This is if you don't check the box of font smoothing on your computer. So you get these jaggy fonts, but they are high contrast, but they're quite jaggy. If standard anti-aliasing, I'm almost too close to it. It's quite blurry, and that's because you're not exploiting the reconstruction filter of the LCD. And ClearType, it makes a little bit of color error, but actually is a bit sharper. To make this just brutally clear, I've turned all the subpixel colors to gray. So I've suddenly made it all monochrome. So you can see there's jaggies and the no filtering. Standard anti-aliasing has this problem that it's forced to tie all 3 of those together at the same value. So you get these funny, clunky things, whereas ClearType makes a little bit of color error, but makes sort of much smoother, sharper fonts. So one last word about gamma correction, which is actually true of all these anti-aliasing, and then we can close and ask for questions. Displays, sadly, are not linear. They don't say, when you say, give me a pixel value half, oh, I'm just assuming all pixels go from 0 to 1. It doesn't actually display sort of half the amount of light between off and on. It displays something annoying like 0.25 or something. That's just the way it is. So what you have to do is you have to do something called gamma correction, where you first apply the inverse function, which cancels it. So you say, please give me a half. It'll turn it into 0.7, which then runs into here and gets back 0.5 amount of light. So they kind of cancel out and makes it be a linear system again, so that all our analysis works. It's really important. It's really important that you do this for ClearType. It's good to do in general, but it's really important for ClearType. because display nonlinearities make power at double the frequencies. That's just a property of nonlinearities. You get these things called harmonics. Turner mentioned it. So here you are, you're innocently trying to display some perfectly acceptable sine wave at a half a cycle per pixel. You run it to the display nonlinearity. Oops, you get a sine wave at 1 cycle per pixel. And remember, if you that hits the color pattern in the display, you get a constant color again. So you're actually reintroducing the color aliasing that you very carefully tried to stomp on with the pre-filtering. So in effect, gamma correction prevents color fringes. And that's, again, if you're sitting at the back of the room, you probably have a better... Actually, I'm too close to this, but if you're far enough back, you'll see this has no gamma correction, and the fonts look darker, but they do have, there's color blotches all over them. You can see them from the back. Whereas here, they're a little bit lighter, but there's no weird color blotches. So in summary, clear type, use the known positions of the LCDs to improve the resolution. And then we use RGB decimation. So you pre-filter the color aliasing, and then you use display sampling to get more resolution. And I just wanted to leave you with the fact that gamma correction is important. And this is sort of a summary of the talk so far, but I'll just let you read that and ask for questions.
So how are this information being incorporated in future products?
How is this information being incorporated in future products? This is completely disingenuous from the man who works for Avalon, but well, we're all working together to try to push things like the clear type and the good anti-aliasing into products like Avalon, which will ship in Longhorn. And there's other side products of standalone rasterizers. I'm pointing to the typography group who's all sitting in a group over here, and they're shipping standalone rasterizers too. So the information is being shared around the company.
You mentioned not just rasterizing, you just mentioned rasterizing. There's also a lot of work being done in 3D graphics. All of those, you also mentioned gamma correction. Is there any Microsoft-wide strategy to unify sort of the filtering, gamma correction, color, tone mapping?
The question is there any global strategy for gamma correction, filtering, all the good stuff? Turner, answer that.
We have several such strategies.
No, right.
There's a question here.
Yeah, if you're using gamma correction here, are you applying that before the signal gets to the frame buffer, or are you using the actual gamma correction as part of the actual frame buffer display hardware? If so, how would you compensate two different contents that might need a different gamma correction?
Okay, that's actually an interesting, difficult issue. I'm sorry. The interesting, difficult issue is, hey, doesn't hardware do like gamma correction or fail to do gamma correction? Or, there's lots of sort of bad... Gamma correction is a giant mess because no one really knows what the gamma of a display is. It's supposed, the display manufacturers are supposed to be doing something in something called EDID, which is, my display has gamma X. But of course, either they just don't do it. As far as I know, they just fail to do it. So...
A lot of the content that assumes a particular gamma was designed for CRTs because there was an assumed industry standard gamma.
2.2.
As a consequence, you got 2.3 or 2.2 or something. Okay. I'm tired. I didn't have any... So what you've got is a whole bunch of content that is fixed, hardwired for that gamma, which is really unfortunate because, now we have displays. LCDs don't have gamma curves. They have S-curve response.
But they fake them up. They often fake them up.
There's an analog circuit inside the LCD that tries to duplicate the CRT's gamma curve, which is really crazy. But it's because of that installed base of content. So now we come along and want some control over how we use gamma, but we're stuck with this content. And as far as I can tell, there's no good solution to reconcile that.
What we do is we treat, at least in the cases I know about, you treat, when someone specifies a pixel, they don't specify half the amount of photons. We assume that when they specify a pixel, they specify it as gamma corrected. And then we, inverse gamma correct it to get the number of photons, do the computations, and then re-gamma correct it. Weird issues, like what happens if you're doing hardware acceleration? Hardware acceleration, I don't know why, but they decided they do compositing, and then no gamma correction. I don't know why. Sorry, this is one of my pet peeves. So we actually, I was working with some of the Avalon folks to sort of go through these horrific contortions back in signal processing to compensate for the fact that there's actually no gamma correction output because we can't control what they do, and they control sort of the actual display surface. So it's a big issue, and you have to kind of, there's no perfect solution. You have to kind of writhe around. And
one follow-up on that, though, is that, for instance, if I'm using Photoshop or some other image application where I actually have applied some hardware feedback loop to set the gamma buffers in the display adapter, and it is, quote, perfect for color reproduction, if ClearType comes along and says, well, I know what my expectation is for that gamma, I will compensate, there's got to be almost no chance of getting that right, unless you have access to that gamma correction.
That's true, although fortunately, sorry. The question is, gee, I've spent hundreds of dollars on Photoshop software, and I've carefully calibrated my monitor, and it's it's beautiful, and now you're going to mess it all up by assuming gamma. Fortunately, it's not quite as bleak as I sort of led you to believe here. You could be, what we do is we take a stab at gamma, and you can be off by a pretty fair amount, and it still looks okay. In fact, one thing we do is we actually under gamma compensate, or at least some of the software does, and there's different branches, there's like n different versions, to kind of get this, see how this is darker than that? People like dark, but they don't like color fringes, so you can kind of push halfway. In fact, what did I do for this? I guessed the gamma of that display. I have no idea what the gamma of that display is. I just said, 1.6, okay, bam. So, I mean, that's sort of typically what goes on.
DLP, John, is linear. Gamma's 1, that's a DLP.
Oh, well, no, they can't be right. Because this has color fringes, right? Or maybe it doesn't. Oh, no. Now you think I'm a total moron. Oh, my God, there are no color fringes. Oh, I'm so embarrassed now. Okay. Well, on my CRT, oh, dear. Okay. Well, yes, okay. So, yes, well, obviously gamma's a big mess. Okay, please ignore this slide. If you actually went on back and looked at this PowerPoint on your CRT, you would see that this is nasty and color fringy and this is not. I can't see because I'm too close. Boy, I wish someone had told me that the gamma was 1.0. Okay, so you can say this is correct and this is over gamma corrected. Okay, well, yes, it's a big mess. Yes? That's a very good question. It turns out that, repeat the question, right. That's your job. The question is, how many PPI or DPI display have to get before, ClearType or anti-aliasing in general sort of is not necessary. You could do a linear system analysis, and you can get answers, but they would be wrong, and here's why. It turns out, or do you want to talk about vernier acuity? There's a slide. Oh, boy, this is so great. What a...
It just talks about the contrast sensitivity.
Right. So there's this thing called vernier acuity, where if you take, it's not shown here, but if you take two little lines, even sort of, below what what your eye is supposed to be able to see, and you misalign them very slightly, you can see it. You can see something is wrong. Your eye is like incredibly, exquisitely sensitive to jaggies, unfortunately. So even you would say, a lot of the people have gone through and have said, at 200 PPI, say the linear system theorists, obviously nothing makes a difference. But we know this is not true. On Bill's, I remember this was like years ago, we had a 200 PPI display, we turned ClearType on, we said, hey, that's pretty cool. It really does work even at 200. I'm guessing, 400? What would you think? Where would you say it would crap out?
600 if it wasn't corrected, probably.
Yeah.
That's a guess. That's a guess.
Yes, so you'd have to have a 600. I guess that makes sense because of printers. So yeah, so you need about a 600 PPI display and no anti-aliasing. That would be fine, but I don't know when that's going to happen.
That's 36 times as many pixels.
Right. It's not going to happen for a while. Our jobs are safe for a while. Yes. Oh, the question is, what would you do differently if you had infinite compute? Oh, that's an interesting question. Well, no, but we don't know how to do. We don't know how to do nonlinear filtering. Probably wider. Well, no, you can't use negative lobes though. You get 10x on hardware, but we're mostly just fighting the quirks of the hardware. Nice text animation, and you get and So because you can do this and still animate things. It's fast enough. You can avoid shortcuts. You can avoid shortcuts you could even probably avoid shortcuts like doing it on alpha. You could probably do the correct filtering on all 3 bands. I don't know. You want to jump in there?
No, I think extra CPU horsepower is totally useless.
Because it's the bandwidth to the display that's the limiting factor.
What we don't
Have is readily usable horsepower intimate with the display. We start getting to the very high resolutions. We start getting into very fast CPUs. Physics, just the wires going through the display, the I²R losses in those wires are the limiting factor right now. So I can get a 10 gigahertz Pentium 7 or whatever I want to put out there, and it's not going to put the horsepower where I want it. But this is a highly opinionated and totally irrelevant.
I think. In fact, you want to do simpler things like we talked about before. You'd rather have a 600 DPI. You'd rather just have paper that just the ink just wiggles and writhes, and not have to muck around with this and just have 600 DPI. But that isn't because of the display. It isn't because the CPU is slow. It's because the pipe to the display is limited and you can't have it. So that's what I want. But oh well.
For ClearType, do you have to worry about the perceived brightness of the colors that you use?
Perceived brightness.
So in other words, green, like the human visual system tends to be more sensitive to green than blue.
Oh.
Do you have to worry with that?
It turns out, there's some slides I hacked out, unfortunately. It turns out you can derive ClearType exactly with that visual model. Sorry, the question is, Chris isn't even here, she's taken off. The question is, do you have to worry about the fact that you're more sensitive to green? Actually, the most important thing is that you're most sensitive to black and white sine wave gratings, and blue-yellow sine wave gratings, if they're tiny, you can't see them. It turns out that's why ClearType works. You can actually derive a version of ClearType based on the contrast sensitivity functions of the different color channels in your brain. And you get essentially a more complicated version than the 3 filters. You actually get 9 filters. You get all 3 color channels are connected to all 3 subpixels with different weird filters. I hacked the slide out. But the 3 box filters or the 3 sync filters are an approximation to the filters, which are, by the way, full of negative lobes, which you couldn't use anyway. So.
Do you have any idea about how increased contrast ratio or resolution, like having 8-bit pixels or 16-bit color components, would affect any of this?
The question is, how about more pixel depth? Would it make things better? You don't really need very much to get. It turns out you don't really need very much to get the anti-aliasing effect. You probably even more. I mean, more than we have now. You probably only need 8 bits of alpha, and then you're totally fine, because you don't really detect differences along the boundaries. Obviously, if you're displaying images, if you're displaying a picture of a sky, and there's subtle gradation of blue, you really want pixel depth. But that's sort of not what we're doing here. We're making sharp little edges, so you don't really need very much. Yep.
Is this technique applicable to high contrast geometry?
Yes, very good question, and the answer is yes. I'm sorry. The very good question, and the answer is goodbye. The question is it applicable to high contrast geometry like lines and sort of Visio art? Yes, both actually. The first anti-aliasing filter and ClearType are both applicable to that. It doesn't really matter that the things are glyphs, other than you can't hint the art. So you can do it, and in fact, various people. We tried it back when we did ClearType. We never really sent it anywhere, and random people have been sort of reinventing it since, but it does work. Interestingly, it doesn't seem to work so well on downsampling JPEGs. And if you have a high-resolution JPEG, or just an image, and you want to just display it at a lower resolution on the screen, it turns out that what the compression does is it tends to lop out all the high frequencies anyway to save bits, and so there isn't very much left to kind of push through ClearType. So it doesn't. You can do it. There's nothing mathematically wrong. It just doesn't seem to help. But for line art, it actually does help.
So I'd just like to add to that. ClearType is, I would expect, better for text because it's only in the horizontal resolution, the direction you get increased resolution, and that fits Western text, which has more detail than
Yep.
whereas line art is typically less.
So the question is, it seems like it would be better for text because it's adding resolution horizontally, not vertically, and that seems like for Latin text. Well, it's interesting. I don't know if you guys want to answer the question about Asian text, or there's this interesting thing. Bill is...
It's a little bit called the tablet, right, where
everything.
You rotate the screen. Sometimes you have a vertical, sometimes you have a horizontal. It turns out that you get a lot of benefit from the type, even with horizontally strike pixels. And it actually turns out the same algorithm will work.
Right, even if you don't rotate them, which is the odd thing. In other words, what Bill is saying, it's probably, this is a not very well understood effect, but you can actually take the subpixels and rotate them without telling ClearType and still display them the same way, and people still seem to like it. I think it's not a very well understood effect. Why? Maybe. This is with, it might be the placebo effect. Was it double blind? Have you ever tried any double blind studies with this or not? I don't know. It might be the placebo effect. I don't know. But the answer is, yeah, Asian text is actually very tricky. It's a very, very tricky thing. Some of these folks here, like Mike, you have to carefully, there isn't enough resolution to display them at low font sizes. So you have to go through and judiciously remove strokes. And then you have to know, oh, okay, a person who reads this language knows that if I drop this stroke, then it's still a meaningful thing. And it's a very, very nasty problem. Because displays still are just not high enough resolution for the folks in the Far East.
We're tackling Asian text with a kind of combination of all of the above. We're actually working on a project just now to do a new Japanese typeface, which is designed to be readable on the screen. The problem you've got is you've got characters like Utsu, you have 8 horizontal strokes, you need 17 pixels to show it. So as John said, you have to throw some of the pixels away. But what we realized we had to do with Japanese was every trick in the book, right? You hint it, you stroke reduce it, you use ClearType, you need it all, in fact. You need to just throw everything at it that you have in order to display really good, complex scripts on the screen.
Because it's such a hard problem. And with the resolutions that we currently have, we really need more resolution.
Yeah, I mean, at 200 ppi, it's not the same issue. But at a nominal 100 ppi, Japanese people read text at the same size as we do, 10, 11 points, all driven by the fovea and the retina. So you can't just make the text bigger, and you don't have enough pixels unless you have the resolution.
But parenthetical comment. Look at the cultural imperialism. We designed the keyboard, and we designed the resolution of the display, and then we're just inflicting on the poor people whose fonts, can't be typed. You can't type the character, and you can't look at the display. It's like.
I find that unaliased text is better on the CRT, but ClearType is better on an LCD, isn't it?
Actually, the question is, what about Courier New? Oh, yeah, it's a special case. I'm glad. It was a shill that I planted in the audience. It turns out Courier New he's saying, gee, Courier New looks kind of nice on the LCD. And why? Well, it all goes back to the fact that when we were doing ClearType, Bill G.
Back even before then, the Courier that Microsoft ships, we originally licensed way back, in the core font days for Windows, was licensed from a company called URW. The Courier was developed by IBM in the public domain, right? URW created the outlines for Courier by
cut off the questions, let everybody leave, and then we'll just.
Well, Courier that you actually see is the product of the golf ball striking a ribbon. It's wider. So the Courier that we had, turns out that at normal reading sizes, the stems are not a pixel wide. Anything takes them to a pixel wide. What ClearType exposed was, in fact, when you turned ClearType on in Courier and you didn't do anything to correct it, the stems almost disappeared. Because, in fact, they were not 1 pixel wide. So Courier is a very special case.
But the story...
Courier
right.
in order to make it work.
The story I like to tell is I think Bill G saw it and complained. And so he ran around and put a special hack in for Courier New to make him happy. Why don't we cut the questions off, because it's 1:25, and then if you want to stick around and ask questions, please come on up and we can let everyone else go. And anyway, thanks.